Good morning, everyone. Today we come to lecture 15. We're still on group theory. And today we'll talk about the group theory of vibrational modes. Okay, so we are going to use a simple example to show you the basic theory. Okay, so we're going to use a simple molecule to start with before we get into MOS tool. Okay, so let's start with a simple molecule. But of course, we don't want the molecule to be too simple. We want some symmetry, and we usually want to avoid too complicated group theory. So let's use the ammonium molecule. I mean, this molecule has nothing to do with our research, but it's just a simple example to educate us about group theory. Okay, so it's not too complicated and not too simple. So what is a ammonium molecule? So if you look at the top view, it is a one nitrogen molecule in the middle, and then connected with the three hydrogen atom. So it's something like this. And then they form an equilateral triangle. Equilateral triangle means all the three sides are of the same length. And this is the top view. And if you view it from a side view, it's like a pyramid. It's like something like this. I think I should use a dashed line. A dashed line. So you have an H atom here. Another H atom. And then the nitrogen is here. So it is connected like this, like a pyramid, But the I mean, not a pyramid. The base is a square. Okay, this is a pyramid with a equilateral triangle base. Okay. The symmetry group is C3V. It's C3V. So let me show you the character table. I think I need to group lecture. Okay, so this is the character table of C2V. So there are totally 6 elements. Okay, 6 elements. So let me write it down. Totally 6 elements. One is the identity element. You have a C3. Yeah, you have a rotation for two times, and then you have the reflection. Maybe let me see how should I denote it. Okay, so let's do it like this. Let me copy this thing. So if you view this, then you can draw the x-axis. Let me use a different color. Okay, you can use the x-axis. X, and then Y. And then you just name this as 1, 2, 3, 4. You just give the number, the label, the atoms. Okay, so let's define the operation. We're going to define the operation. Let's deal with this later. So define operation. So A means sigma X means A. Both big A and small a means reflection. X go to negative X. Okay, X go to negative X. Okay, then later you have this this you call this axis the A. You call this A. Okay, this is the reflection plane. Then you call this B, and then you can call this C. Okay, so then correspondingly you have this B means B of B, reflection with respect to axis B. So the same for C or small c, reflection with respect to axis C. Okay, then we're going to define D. D basically means C3, rotation. Counterclockwise for 120 degree. And then the air is just 2 of them. So we are going to we're going to use a small d and a small f. So later I'll tell you why we use 2. Okay, identity operation. Okay, so this C3V basically has this element A, B, C, and then D and F. Okay, so these 2 are just C3. This is a class. Class. This is a class. These are classes. Okay, so there are 6 elements. 6 elements and 3 classes. 3 classes. Okay, so these are the basic property of this C3V group. Okay, now we're going to study the motion of these atoms. We'll study the motion of these atoms. Okay, so let me copy this. So when you study the motion of atoms, so each atom, we label them as 1, 2, 3, 4. 1, 2, 3, 4. And then for each one, we're going to define a vector. This vector is arbitrary. Like it just we use this as a U1, U1. This is a U2. This is U3. And this is U4. All these 4 vectors are arbitrary. It just denotes arbitrary vector at this particular atom. Okay, that represent the motion direction of this atom. Okay, then the whole physical space of the motion of atoms is, you can use this side to represent them, is U1, U2, U3, U4. Okay, but of course, for each one of them, you have X1, Y1, Z1. So this one you can denote it as X1, Y1, Z1. So basically for this, you just have Xi, Yi, Zi for all of them. So I equal to 1, 2, 3, 4. Okay, so let's just write all of them. 2, X3, Y3, Z3, and X4, Y4, Z4. Okay, so totally the degree of freedom is 4 atoms times 3 degree of freedom per atom. So it's totally 12. Okay, this is always the case. You count the number of atoms for the molecule and times 3. That's the total number of degree of freedom. Okay, so we want to find the representation. We will find the representation of phi. So this, you can treat this as an object. This object is basically this thing, this structure. Okay, for each atom, you have a vector attached to it. Okay, and then they form a certain space, and this space has its own representation on this symmetry group, and we need to find the space, and we need to find the representation. It is a reducible representation. Okay, and we're going to find it. So do you know what we're going to do? Okay, so then we're going to see how this thing transforms under every operation. Okay, we're going to find how this thing transforms under each operation. So let's consider how phi transform under the elements of C3V. Okay, so let's find A, U1, U2, U3, U4. So let's consider the sigma v. Let's consider sigma v. So sigma v is what? Sigma v is this one. Okay, this one. Okay, let's consider A. So A, basically you just change x into negative x. Okay, so and also let's consider this. Let me just copy this thing. Okay, copy. Where should I put it? I just here then. Okay, so A, under A, x will go to negative x, and 1 will go to 2. Okay, you can see that, right? If you make a reflection here, x will become negative x. This 1 and 2 will exchange, and 3 and 4 remain the same. Okay, remain the same. Okay, so yeah, x to negative x. Okay, so 3 and 4 are just the same. So this is what it means. Okay, so this thing will become, so each of them is going to transform. First, U2 and U1 will exchange. Okay, this two will exchange. So you can see this. This one will go here. This one will go here. Okay, so just according to this transformation, because the atoms switch position, and then each of them is going to have an A here. A. So what is A? So A is acting on X, Y, Z, and then it will become negative X, Y, Z. Because this is A. Okay. So this will be negative 1, 1, 1, 0, 0. Is it okay? So you need to once you apply A on this whole space, all the atoms, they will change position according to here, and every vector is going to flip the sign of the x. So for every vector, you apply the small a. The small a means reflection on the vector. Then this atom change position. Is that okay? Is that okay? So we're going to write it out. So you're going to have a 4x4 matrix, 0, A, 0, and then 0, 0, 0, 0. Okay, then not enough space. Let me shrink it slightly. Okay, so you can just copy this. Okay, so this is A. This is A. Okay, so what is the character of A? Of A in this representation. let me call gamma. Let me call gamma, as this representation is gamma. Okay, so chi A in gamma is basically you can this, you're going to sum over two number of A. Okay, it's going to number of A in the diagonal position. Okay, times the trace of A. So if you write this out in a complete form, it will be something like this. It will be something like this. You basically you just copy this thing. You just copy this thing. Copy. And then you just paste it here. Paste it here. Paste it here. You need more space. And then you're going to paste it here. Let me see. Okay, so then all of these are 0, 0, 0, 0. I mean, if you want to write more rigorously, then you have all this here. Okay, these are all 0. Then of course, if you want it to be faster, you just copy. You just copy. Okay, so the whole matrix is look like this. Okay, so the whole matrix look like this. Okay, so what is the character? The character, you just you sum over the character is basically this thing. Okay, so the character, this is A. Okay, so character is basically -1 + 1 + 1. This is 1 unit, and you times 2. So it will be just -2. Okay, so basically, is the number of A, the number of A in the diagonal position times the trace of A. Okay, times the trace of A. Okay, so the number of A is 2A. So each trace, the trace here is -1 + 1 + 1 is -1. So -2. Is it okay? Is it okay? Huh? Oh, sorry, +1. My mistake. Okay, +1. +1. So this is +1. So this is +2. Yeah, that's a mistake. +2. Okay, is it okay? Not difficult, right? Okay, let's do more. Okay, so I mean, doing this kind of in detail so that you kind of know the flow, but later we can move faster as you get used to it. Okay, so let's consider. Once you know this, then you don't need to do B and C anymore. You don't need to do B and C anymore because they belong to the same class. So all the elements in the same class, they have the same character. So let's go to deal with this class, deal with D. Okay, so what is D? D is rotation. D is rotation. So you just copy this. Okay, so consider D. So this is C3. C3 operation. Then this one is basically you just a rotation. A rotation 120 degrees. So when you go to D, and then you apply on U1, U2, U4. So what? Okay, let's consider the D. The D rotation. I think I should make it simpler. Let's make it simpler. We don't need this. Can I draw a triangle? Oh, okay, yes. Okay, not very good. Let me do it again. Okay, something like that. Okay, so you have 1, 2, 3. Of course, the 4 is in the middle. Okay, now you go 120 degree rotation. This is D. Then it will become basically the same thing, but all the numbers are rotated. So this will be 1, 2, 3. So that means under the D operation, 1 will become 2, 3. And 2 will become 1. And 3 will become 2. And then 4 is just the same as 4. Okay, so you're going to have 1 become 3, right? So you're going to have U3 here. 2 become 1. So you're going to have U1 here. And then here, 3 will become 2. So you have 2. Then you have 4. Okay. But for each vector, you're going to have the rotation. So we're going to add the rotation D here. D. So what is D? What is D? D X, Y, Z. It will be represented by this matrix. Okay. Okay, here I won't bother confirming it. But it should not be difficult. You just have a rotation. So once you have a rotation, the X, Y will mix together. Okay. So this is the transformation for the X, Y, Z under 120 degree. Okay. So when you write it down, you're going to have this is 3, right? So you're going to have 0, 0, D, 0. Okay, so then this will be D 0, 0, 0, 0, D 0, 0, 0, D. Then need to make it smaller. Okay, so copy this. Okay, so this is the representation. And then the trace of D will be -1. -1 plus 1 will be 0. Okay, so now let's get the character. Okay, what is the character? Then we basically just copy this thing. Okay, so what is the character? So what is the character of D in this representation? So you just replace of this, the number of D in the diagonal and the trace of D. In this case, the trace is 0. Okay, and the number is also, the number is 1. You only have 1. You only have 1 D. Okay, so this will be 1 times 0. Then the result is 0. Okay, is 0. So let me delete all of this. Okay, is it okay? So now, let's go back. Look at this character table. So I'm going to draw this, copy this character table. I'm going to copy this character table. Oh. So in this character table, there are C3V. I'm just writing it down now. Okay, so in this character table, you have the E element, you have 2C3, and then you have 3V. Of course, these two are just D and F in our case. And this will be A, B, C. And then you have A1, A2 representation. So all of this will be 1, I think. 1, this will be 2. Okay, then this 1, 1, 1, -1, -0. Okay, now let's write down the gamma. So the gamma is how many for E it will be 12, because E is the identity operation. So basically you just ask the dimension. What is the dimension? I mean, here you can see. Okay, totally it will be 12. So identity element, just all of these are 1. All of these are 1. Okay, so the character for the E will be 12. So what about for the D and F? We already got it, is 0. Okay, 0. And then for this is ABC, we got it. That is 2. That is 2. Okay, so these are all the character. Okay, so we're going to decompose this gamma into different irreducible representation. So we're going to deal with this, the number of A1 in gamma is, so you have this formula, using the formula of decomposition. Composition. So basically the number of representation I equal to, you have a total number of H, and then you sum over class. Okay, you have a character of gamma, and then you have a class K. And then you have gamma I. And then you have this class. Okay. Sum over classes. I should write it. Number of chi I, not chi I, is representation I. Number of the I representation in gamma. And then here you times the number of elements in class K. I hope you still remember this formula. Okay, we proved this a few lectures ago. Okay, so it's pretty simple. Then we just do it. It is better if we move this away. Let me just move it away. Let me just move it away, because then we see the character table much better. Okay, so here it will be just the number of elements will be 6. The total is 6 elements. Then you sum over 1 times 12. 1 times 12. 0 times this will be 0. 1 times 2 times 3. So 1 times 2 times 3. So this will be this will be 18. This will be 3. Okay, this will be 3. And then the number of A2 in gamma. Then you 1 times 12 plus 0, -1 times 2 times 3. So this will be -6. So this will be 1. Okay. So the number of E gamma will be 2 times 12, 0 plus 0. Because this is 0, 0. This will be 24. So eventually you have 4. Okay. So gamma equal to 3A1 plus A2 plus 4E. Okay, plus 4E. So this is the decomposition. So, okay, now let's move this back. Let's move this back. Okay, okay, so let's consider what does this include? What does this include? What does this include? It include 3 translational motion, and 3 rotational motion. And then let me see. Then it will be 6 vibrational mode. So what do you mean? What do you mean? Okay, so let's go to let's get this Let us get this molecule. Okay, let's get this molecule. So translation means, okay, translation. Okay, let's. Translation means all of this, they move in exactly the same direction. Okay, or you can make it go to X, Y, Z, go up. All of this go up. You just move the molecule around. Okay, so this one are not interesting, just translation. So they're trivial. They're trivial. Okay. So what does this represent? They will transform this they will transform as X, Y, Z. They transform as a vector. Because they just move up and down. They just transform as vector. So we can already know the representation. Okay, here I didn't write this, but here you have this linear function. You have this linear function Z, Z2, X, Ry. So look at here. This is the transformation mode, the representation for Z and XY. Okay, so you can see that translation will occupy two irreducible representation, A1 and Z. Okay, A1 and Z. So we can kind of know, they will occupy A1 and Z. Representation. Should not say occupy. They have representations. Okay, so you look at the table, you know. Okay, so another one is rotation. So rotation is this whole thing just rotates. Okay, so how do I represent rotation? This one, you can have this, and then you have this, and the whole thing just rotates. Okay, this is also one motion. So in the representation in the table, these are the RZ, RX, and RY. These are the rotation along the Z-axis, along the X and Y axis. If there's a rotation along Z-axis, then it is A2 representation. If it is a rotation along X and Y, X or Y axis, it will be the Y representation. Is it okay? So, I mean, you can have different mode. Maybe I don't know what the right vector is for the X and Y. Okay, so you can have that's weird. Let me copy again. So you can have a rotation. Maybe if this is the X-axis, then the rotation will be something like this, something like this. Okay, rotation. It may not be accurate here. I just randomly draw it. Okay, so they will have A2 and Y representation. They will occupy A2 and Y representation. Okay, so then we can already write this out. So you can write it out as A1 plus E plus A2 plus E and plus you have 2A1 and then 2E. Okay. So decompose it. This will be translation. This will be rotation. And this will be, the rest are all vibration. The rest are all vibrations. So these are the decomposition. The decomposition of vibration. Is okay? Do you have any questions? Okay, how do we do it? How do we move from here? Okay, so after you do that, you can go and have a look. Go and have a look at the table. Copy. To see the property of these vibrations. Okay, you have 2A1. So you have two of them, vibration, and 3E2. Okay, so these are the vibration. Okay, these are. There's no A2 vibrational mode. No A2 vibrational mode. So these are the transformation property. You can also write a little bit more here. So these are the representation, the function. Okay, so I think we'll maybe use another lecture to talk about Raman and infrared activity. But now I just tell you the result first. Okay. If a vibrational mode transform like a vector, it is infrared active. Active. Okay. Rules, Raman and infrared activity. You can say rules Okay, rule number one, if a vibrational mode transform like a vector, it is infrared active. Because the infrared activity is induced by an electric dipole. And the electric dipole is a vector. Okay? And if a vibrational mode transform like a tensor, it is Raman active. Transform like a tensor. It is, maybe I should use some color to represent it. Like a vector, it is infrared active. This one, maybe use red. Like a tensor, it is Raman active. These are the rules. Probably I'll use maybe another lecture to explain why this is the case. But for now, you just remember these rules. Once you remember, then it's very easy to know whether a mode is Raman active. Infrared active means you shine the infrared light, you see the infrared absorption of that phonon. Raman active means you shine the light, you see a Raman mode. It is just that simple. Okay. If you know whether you will be able to see this phonon mode by Raman, you just look at the symmetry property of this phonon mode. So let's look at A1 mode. Does it transform like a vector? Yes, because you see the Z here. This is part of the vector. Okay. So, and does it transform like a tensor? It's also yes. These are tensor elements. Okay. So you can okay, with x, y, z, you form a vector, and then you have x, y, x, z, y, x, y, 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 z, z, x, z, y, z, z. Then you form a tensor. And this is a general, this is a general tensor. You can decompose this tensor into a symmetrized part and the anti-symmetrized part. And after you decompose it, all those things will come out. Okay, so these are the tensor elements. Okay, if you decompose this thing into the anti-symmetric and symmetric part, then all this combination, this thing will come out. So these are tensor elements. Okay, these are and these are vector. I should not say element. It is a vector component. So these are, yeah, this can be tensor elements. Okay, so A1, so A1 transform like a vector and also like a tensor. So this is both IR and Raman active, because it has both. And E also has both. It also has both. So this one, I point it like here. Okay, both IR and Raman active. Okay, usually for a molecule with low symmetry, the phonon mode can be both Raman and infraactive because the symmetry is low. Okay, once you go to a higher symmetry system, particularly those with the inversion symmetry. Every group with the inversion symmetry, the infrared and the Raman, they're exclusive. If you have a particular group like graphene, it has inversion symmetry, then the infrared and Raman mode, they're not going to overlap. They're exclusive. They're exclusive because the vector and the tensor, they don't transform in the same way under inversion. Vector, because you can easily tell. You can easily tell the tensor is basically two vector put together. It form a tensor, right? So under inversion, V will become negative V, but the tensor will just be the same. Because negative V just VV. Okay, so they will never share the same representation under inversion. Okay, so vector and tensor transform differently under inversion. So that means for a molecule with inversion tree, the IR and Raman active modes are exclusive to each other. That means if you have a system with an inversion symmetry, if a certain phonon mode is Raman active, it is not infraactive. If it is infraactive, it is not Raman active. This is a property for the system with the inversion symmetry, and it is dictated by symmetry, by group theory.
That's why 3R.
Then I don't know. You need to look at the symmetry. Okay, so the rule is actually quite simple. So let me summarize what we have been doing. First, when you have a molecule, you just write down the representation for the motion space, and the degree of freedom is the number of atoms in the molecule times 3. Okay, and then you just write down the character for this representation. Write down the character for this representation. You decompose it according to the formula that we use. You decompose it, and then get the decomposition. In the decomposition, you take away the translation, you take away the rotation, and then the rest are just vibration. Then you will be identify how many vibrational modes, and then you just check each mode whether it is Raman active or infraactive. So this, yeah, you don't even need to calculate those modes, the displacement vector. You don't even need to do that. You just from the symmetry, you already know how many vibrations are in this molecule, and which one is Raman active, which one is infraactive. You don't need to calculate the vibrational vector, those things. Yeah. So the power of group theory is that you can all save all those calculations. You can already know some main results just from the symmetry. Is it okay?
So is the vector always follows the symmetry, right?
What do you mean?
Because you started from to analyze this representation, C to V in this case. So is there any possibility to add symmetry is different from the lattice?
Different from the lattice? What do you mean?
So if we can suppose start with different symmetry to analyze this vector. Is there any possibility to start with different symmetry?
I don't understand your question. I mean, the symmetry group is the group for the molecule, and it is there.
But this means any
This symmetry group is specific for this structure.
Yeah. If you have another structure with the same symmetry, then you get something similar. But of course, because the number of atoms are different, you're going to get different combinations. Not just the symmetry. Here we construct a space, and the space depends on the number of molecules. This is the space that we construct. I mean, not this is transformation. This is the space that we construct. This depends on how many molecules, how many atoms are there in the molecule.
was it for crystals?
Yeah. Okay, let's do a crystal. Okay, so now let's do MOS S2. Okay, are you okay with this one? Okay, let's deal with MOS2. Okay, so I mean, from this you kind of know the by the way, one thing is that I forgot to mention this. There's a way that you can further simplify it. That is this trace of A. This trace of A you can directly obtain from the character table. Here we're writing it out, and then you sum over this. Okay, but you don't need to do it because from the character table you know Z and XY. You know how a vector transforms. So the trace is just this one plus this one. That's it. Do you know what I mean? So for example, let me copy this. Let me put it here. So if you want to know the representation for vector, then all you need to do is, this is Z, this is XY. So they transform according to A1 and E. So basically, here this is already determined. This is A1 plus E. Okay, it's this one and this one. Okay, so the trace it will be just this one plus this. Okay, the trace is 3. And then this one plus this will be 0. And this one plus this will be 1. Yeah. Okay. So we can easily check. We can easily check. Sorry, I keep going back and forth. We can easily check. What is the trace of A? The trace of A is just 1. Okay, it's just 1. And then the trace of D, the trace of D is 0. Okay, so and then it is just the same here. This is the trace of A, and this is the trace of D. Do you know what I mean? Because this is D, this is A. And how a vector transform? The vector just transform as this sum with this. So all you need to do is the sum the character. Sum the character, then you get 0, you get 1. Okay, so you get this the trace can directly from the character table. Is it okay? Is it okay? You get it? Chun Hung, you get it? Looks like you're quite puzzled.
It looks like so E has the X and Y component and A1 has Z component.
Yeah, so the whole vector, this whole vector transform as A1 plus Z. So if you write it down, it will be, you will have a X, Y, Z. Then this will be a block form. That is Z. This will be another block form, that's A. Okay, so the trace of this one, the trace of this one is -1, and the trace of this one is 1. So you get a certain trace -1. This one you get the trace 1. So so the total trace is -1 plus 1 is 0. So that's why you get 0. I mean, you can easily tell. You can easily tell. This is how the D transform. You have a Z here, and then you have an A here. So the XY transform in one way, the Z transform in another way. So this Z sum together, you have -1. This one you have 1. -1 plus 1, you get 0. Do you know what I mean? So this is why you have a -1 here, you have a 1 here. Okay. So the same for A. For A, they transform as an A and also E. So you can actually see it here. For the A, it XY transform as a E. And this one as an A. So this is 0, this is 1. You sum together, it's 1. Do you know what I mean? So you have 0, you have 1, you sum together is 1. Is it okay? You can write out the matrix. You get the answer, but you don't need to do so. You just from the character table, you sum over it. You already get the answer you need. This will save you some trouble, but because I want to illustrate you how it works, so that's why I write down the matrix. But after you know the principle, you don't need to write down the matrix anymore. Is it okay? Okay, so let's go to MOS2. Let's go to MOS2. Let's go to monolayer MOS2. So the monolayer MOS2 is something like this. You have the MO atom, and then on the top is like this, top view. The top view is something like this. The top view is like a piece of graphene, and the side view is for every MO atom. Basically, you have you have the MO atom here. For every MO atom. MO. And then you have the S atom. I mean, I should draw it bigger. Okay. So on the side view, you actually have one MO atom, and then you have the S atom. Okay, you have the S atom. Go like this. Okay. Go like this. So basically, you have a graphene lattice, but for every S atom, you have one on top, the other in the bottom. Is that okay? Okay. So then let's label it. You are going to have one here. You have a 1 here, and then this will be 2 and 3. So 1, 2, 3. Is that okay? The 2 atoms are on top and bottom. But since it is a lattice, all of these are all 1. Okay, because in a phonon mode, all of these atoms in the unit cell, they are moving in the same direction because you preserve the periodicity. Okay, so all of these are going to move exactly in the same way. Okay, the same for the 2 and 3. Once you define the vector in one unit cell, you are going to have exactly the same displacement for all the atoms in all the unit cells. We are considering gamma point. Consider gamma point phonon. In which we for this we only need to consider the vibration of one unit cell. Okay, you only need to consider the vibration of one unit cell because all the unit cells they vibrate identically in the vibration. Okay, so now we're going to also consider each of them. You have a U1 and U2 and U3. Is that okay? So you just take this unit cell. You have different ways to view the unit cell. You can view the unit cell in this way. But that might be difficult for you to view the symmetry. Okay, so we are going to view the unit cell in a different way. Okay, I'm going to take this unit cell. I'm going to take the unit cell in this way. I'm going to take the unit cell. I'm going to take this. Okay, I'm going to just cut one hexagon as a unit cell. Is it okay? And then the point group will be with respect to the middle. Okay, with respect to the middle. Is okay? So you are going to have certainly you are going to have C3 rotational symmetry. You're also going to have like a vertical symmetry. So this hexagon, all of these are the same atom. Okay, they're the same atom. You reflect, you go to the same. Okay, so now let's go to the symmetry group. The symmetry group is actually I forgot to show you the vibrational mode of the ammonium. Okay, we will deal with this later. Then I prepared this, but I didn't show you. Okay, anyway, we're already in MOS2, so let's move on with the MOS2. When we have time at the end of the lecture, I go back to show you the animation of the ammonia. Okay, so now I already did the calculation for you. but for the sake of your clarity, so let me just do it one more time, and then we just move from there. Okay. How many? There are totally 6. So there are 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 1, 2. Okay, so this is a D3H group. How many elements do you have? You have totally 12. So each of them, this is an identity element. This is a mirror reflection on the horizontal plane. This C3 rotational symmetry. This is I think this is a rotation plus the reflection. You rotate 120 degrees and then reflect. This is the rotation on the plane. And then this is the mirror on the vertical plane. Okay, so you have this mole A1 prime, A2 prime, E prime, A1 double prime, A2 double prime, E double prime, E double prime. So for A11, is all are the same, but for A2 prime, this is -1, this is -1. Okay. So let's continue. 2. And then we have A1 prime. The main difference is that you're going to have the mirror reflection that is negative. Okay, -1, -1, -1, -1. Okay, I'm copying this table. Okay, so now I just copy this table. Okay, and we're going to calculate. We're going to show how a vector transform. We're going to show how a vector transform. Okay, let me get some space. So we're going to get the trace, the representation of a vector. Then you just go back and look at here. So I already highlighted for you. The vector will transform as a E prime plus a A2 double prime. Okay, so yeah, a vector will transform as a E prime plus a A2 double prime. Then you can already get the trace. Okay, you get the trace. So this one and this one, then you sum over it. You get 3. And then this sum over, you get 1. This sum over, you get 0. This sum over, you get -2. This is -1. And then this is 1. Okay, so this is the trace when you transform a vector. Is okay? Okay. So now let's get another one. The number of what is it called? Is it called the number of atoms whose position remain unchanged by symmetry. So what do you mean? What do you mean? This means here. So let's go up. This means once you do the transformation, how many of this appear in the diagonal elements? So that means when you apply the rotation, how many atoms remain unchanged? Like it doesn't move to another position. In this case of this A, you can see that this 1 and 2, they exchange position. the exchange position. So that's why they are off. Because the exchange position, this will be 0. And this 3 and 4, they are the same. So that's why you have this 2 here. So you're going to do the same thing for MOS too. Okay. But in this time, if the MO atom go back to MO atom, it is the same, even if we go to a different unit cell. Okay. So the only difference for the lattice is that when you apply the rotation, if the atom go to another unit cell, but it is the same thing, the same atom, it is the same. That's the only difference. Okay. Okay, so now let's consider this unit cell. Okay, let's consider this unit cell. You have MO, you have S, you have MO, you have S. Now this one you have to count it. There's no shortcut. I'm sorry, my drawing is just very bad. Hopefully I draw it better. Okay. This one is not part of your symmetry. You just need to know. Okay. This one is not part of the symmetry. This one is the configuration of your lattice. Okay. So maybe this one should be yes. Okay, let's deal with it one by one. Let's deal with it one by one. So for identity, then it's simple. You just get 3. Because you don't move. There are 3 atoms in the unit cell. They just overlap. So 3. So this vertical one, what you will do is you have a MO atom, and then you have a S, you have a S. So this is the mirror reflection. Okay, this is the mirror reflection. So they have 1, 2, 3. So for this one, this one will become 1, 2 will become 3, 3 will become 2. So how many atoms remain unchanged? There's only 1. Okay, there's only 1. So this thing will be 1. Okay, so let's go to rotation. This is a C3 rotation. Once you rotate, then the MO will go to MO, the S will go to S. Okay, so what's the number? Can someone tell me? What is the number of atoms remain unchanged and the C3 rotation? Can someone tell me? 6. There are only 3 atoms. Why is 3? Yeah, so because the MO go back to MO, so you just go back to itself. The 2S also go back to the 2S, so it is 3. Is it okay? Can you follow me? Okay, now let's go to the 2S3. This 2S3 means you rotate. It means you rotate this and then this. You rotate 120 degrees and then do a reflection. Okay, if you do it like this, once you contain, you rotate, you go back to itself. That's fine. But once you do this mirror reflection, the 2 will become 3. 3 will become 2. So these 2 we change position. The only thing that will remain the same is 1, 1, 1 to 1. Is it okay? Is it okay? So can someone tell me the number? What is the number for S2, S3?
1.
Yeah, it will be 1. Okay, good. Okay, this is a C2. What does it mean? That means you draw a line here, and then you're going to make a rotation like this. 180 degree rotation. So can someone tell me what is the number? Another option? Give me a number. 1, 2, 3. I hear 3 answers. Oh, you just do it. Okay, you just do it. The MO will go back to MO, right? So you at least have 1. Okay, now the problem is, how is this go to here? Okay, here you have a S in the bottom. You have a S in the bottom. Let's say this is a 2 and 3. And then after this 3 rotate, you go to here. The 2 rotate, you go to here. You know what I mean? You know what I mean? It's a rotation, not reflection. If it is a reflection, then this one will go to here. This one is go to here. This is reflection. Rotation means this one will go to the bottom. This bottom one go to the top. Yeah, you have 2 S atom, one on top, the other in the bottom, right? You're making a rotation, right? Okay. Okay, so this really you need to have some kind of exercise on how to visualize the operation. Is okay? So how many? Can someone tell me? What's the number here? Huh? 3?
2.
2?
1.
Okay, it looks like you don't get it. Okay, let me explain one more time. We're trying to get the number of atoms whose position remain unchanged by symmetry. So each atom has a number. Okay? Okay, they have a number. Now when you can see the rotation, okay. So let me draw it one more time. Okay, let me draw it one more time. Okay, so yes. So this is 1. This is 2, 3. So each of them is like this. So you have a S here. This is still 2. This is 3. Okay. So now you make a rotation. You make a rotation. The MO will remain the same, right? So MO just become MO. But this S2 here, after rotation, the S2 after 180 degrees will go to here. And then this one will go to here. Is okay? So this one will be S3. And then S3 will become S2. Is okay? So that means when you do this operation, what is this operation? C2. When you do the C2 operation on U1, U2, U3, you are going to exchange MO is U1. You have a C2. Then this will become U3. And this will become U2. So if you really write it out, it will be Z2, 0, 0, 0, 0, Z2, 0, C2, U1, U2, U3. So how many C2 are in the diagonal position? 1, right? Okay, you get it now? You get it now? If you don't get it, then do an exercise. Okay, so there's only 1. Okay, I hope you. Okay, I hope the next question, all of you will be able to answer me with the correct answer fast. Okay, your last chance to show that you understand. Can someone tell me this number? This is a reflection on a vertical plane. Give me a number. I mean, 1, 2, 3. One of them, because there are only 3 atoms. Well, she said 3. Any other options? Any other? Huh? By the way, the one on Zoom, you can also answer. We have 3 silent audience online. How about you tell me an answer? Are you there? The one on Zoom. Okay. Those 3 people on Zoom. You have an answer for me? What is this number here? Nobody answers. Okay, I don't think they're there. Okay, those on Zoom. Are you still there? Can you give me
Yeah,
an
I'm
answer?
here, but I don't understand.
What about the other two? I mean, there's only one way that you can make it work. Okay. So, Tianyi, why are you not understanding? I mean, which part? Which part is so difficult? Huh? Okay. Okay, let me see how I can. Okay, if you still don't understand, go back to watch this video again and again until you understand, because it's nothing difficult. Okay, it's not even physics. It's just it's just you have I mean, it's really not physics. It just you have a certain configuration. You make a symmetry operation, and how many atom overlap, that's it. So okay, here you do the reflection. You do the reflection. Okay, let me copy this. Let me copy this. You do the reflection. I mean, there's only one way you can make it work, because if you do the reflection here, the MO is going to become S. It's not a symmetry operation. A symmetry operation means at least MO go to MO, S go to S. Okay. If you do a mirror, operation, then it's just a direct translation, and not translation. It's just a mirror. You put a mirror in the middle. This one will go to here. This one go to here. The MO is the same. So how many atoms will remain the same? Yes, 3. So Tianyi, do you get it now? No response.
I try to.
But which part is so difficult? Huh? So basically, this question is, you have this configuration. I apply a mirror reflection. How many atoms have exactly the same position even after this operation? You have 1, you have 2, you have 3. So if you do it, then you'll find that after this, 1 will just become 1, 2 will just become 2, 3 will just become 3. Then so all 3 of them remain exactly the same. Is it okay? Is it okay? No, I think one reason is because when you're on Zoom, it's very easy that you lose the attention. And that's why I encourage you to come to the room and listen to the lecture, because this will help you to pay attention. I mean, I understand that on Zoom is more convenient for you, but it's not good for your learning, because you easily lose the attention. So I mean, I can see all 4 students, postdocs, inside the lab. They know what I'm doing, but it looks like the 3 on Zoom, you get lost already, because it's all about attention. It's not whether the problem is difficult or not. Okay, but I mean, you're free to choose on Zoom, but I would say it would be more efficient for you to focus. Okay, otherwise you need to rewatch the video and still take your time. Okay, anyway. Okay, I hope you're okay with this. Is it okay? Is it okay? Okay. So I mean, those on Zoom. Okay, I hope you're not offended. I don't try to blame you. I just give you the suggestion that, yeah, you on Zoom is easy to get distracted. That's why you cannot answer the question. Okay. But anyway, if you don't get it, rewatch the video so that you know what I'm doing. Okay, because I think this will be if you later you do any research involve Raman or infrared spectroscopy, I think this kind of knowledge will be useful for you. Okay, so here will be 3. Is okay? Okay, so then the next step, I need to move this away. Okay, so next step is to really get the character for this, I should say phi is the motion. Let's just say motion then. I don't know what I should write here. Is the atom motion. Okay, so this is the representation. So it's very simple. All you need to do is to times this together. Okay, times this together because I mean you know what we have been doing, right? Okay, so okay, I hope you remember this. Where is that thing? Sorry, I keep going back. Okay, so we're doing a trace like this. Okay, so for each of one, you already get the character. Then you just count how many of them repeat. Okay, so basically for this formula, the number of A in the diagonal element times the trace of A. Okay, this is what we're doing. So all you need to do is just the times this. It's just that simple. The algebra of group theory are all very simple. The difficult part is the concept. Okay, you need to get the concept. Okay, so then this will be 9, and then this will be 1, 0, -2, -1, and 3. Okay, so that is the character. Okay, you get it? Okay, so now we're going to do it one by one to decompose it, and it's not difficult. It's not difficult. So they're all very simple. So let's do it quickly. Even if I do it multiple times, it's still very fast. Okay, in order to accelerate, so let me just cut it. Okay, so A1, the number of A1, okay, will be, so there are totally 12 elements, right? It will be 9, 1, 0. Sorry. 1, this will be 2, so this will be 0, -2 times 2. And then this is 3, -1 times 3, and then 3 times 1 times 3, so it will be 3 times 1 times 3. Is okay? You just times this, and then also with this number together. And then what do you get? You have 10 here. 10 minus 4 is 6. 6 minus 3 is 3. Why is it not the same? Let me see. This is 6. This will be 16. What? Oh, yeah. 19. Okay, -4 minus 3 will be 12. Okay, so 12 over 12 is 1. Okay, so okay, let's do it together. Then it will be 1. Okay, so the number of A2 prime will be this will be 9 plus 1. This will be 0. Okay, this one is easy. 0, always 0. And -2 times 2. And then plus 1 times 3 plus -1 times 3 times 3. Let me see. 10, 6, 9, 9. Okay, so it will be 0. will be 0. Okay, E prime. So you will be, this will be 19, 2, 0. Then it will be 2 times 2. 2 times 2 will be 4. Then it will be 0. Okay, all these are 0. Okay, so this will be totally 24. So this will be 2. Okay, so let's continue. Okay, 9 minus 1, 0. 2 times 2. And then, let me see, is it correct? 0. 2 times 2, okay. Negative, this will be negative 1 and negative 3. Negative 3. Oh, sorry, negative 3 times 3. Times 3. So this will be A 12, 9, 9. Okay, so this will be 0. Number of A2 double prime. Okay, 9 minus 1, 0. This will be 1. 1 times 2 is be 3. 3 times 3 will be 9. So this will be A 12, 15, 15, 24. Okay, 24. This will be 2. Then the number of E prime will be 18 minus 2, 0, minus 2 times 2. Then it's all 0 here. This will be 1. Okay, so eventually, this equal to how many? Will be A1 plus 2E prime plus 2A2 prime. Okay, so this is the decomposition. Is it okay? Is okay? I mean, all the algebra, they're very straightforward. Nothing difficult. I'm just hoping that you understand the concept. Okay. Okay, so now 3 of them correspond to simply translation. Okay, so what are they? These 2 are translation. So E1 and A2 prime. E prime and A2 prime. So E and A2 prime. So these 2 are translation. What do you mean translation? That means you just move the whole lattice in one direction. That's it. And in the phonon band strata, that corresponds to the acoustic mode. Okay, the acoustic mode at the gamma point just means translation. Okay. Not E prime, A2 prime, not 2, just 1. Okay, and all the rest will be A1 plus A2 plus E prime and E double prime. So these are acoustic mode. Acoustic mode. These are optical phonon mode. Is it okay? So how many phonon branches do you have? So 1, 2, 3, 4, 5. I mean, you have totally 9. So totally 9 branches of phonons. Okay. 3 acoustic mode. 3 acoustic mode. And you already know that. And you already know that is 1 is A2. The others 2 are the degenerate. Okay. Then you have 6. You have 6 optical mode. You have 1A1, 1A2, and then you have 2. These are degenerate. The same. E double prime. Okay. So these are the phonons in MOS2. You don't even need to do any calculation on those displacement vector. Just from group theory, you already know the composition of the phonon mode in monolayer WSC2 and their symmetry properties. Okay. So so you can also know their Raman activity. So let me copy this thing first. Okay, I'm going to ask you a question again. Hopefully you can answer me. This IZ means rotational mode. Okay. Okay, so look at our answer. Our answer is A1. A1. I think there's an A1 prime. All of them has prime. Yeah, all of them has prime. Okay. A1 prime, A2 prime. Okay, let me see. These are phonon mode. A1 prime, A2 prime. These are optical phonon. Okay, I think that's the case, right? A1 prime, A2 double prime, E prime, E double prime. These are optical phonons. Okay, then just tell me which modes are Raman active, which mode are infrared active. Okay, give me the answer. Hopefully you can do it immediately. A1 prime mode, infrared or Raman. Okay, so good. Okay, so this will be. Okay, this one, infrared or Raman. Okay, there's nothing. That means it's not infrared active, not Raman active. So this what we call the silent mode. That means you cannot see it at all. You measure infrared, it's not there. You measure Raman, it's not there. So this is a silent mode. Yeah, is it okay? So it doesn't mean you shine the light, measure the Raman, you see everything. Some of the phonon mode are hidden. Okay, you do this from the symmetry property. And that is actually correspond to a certain rotational mode. But for lattice, they don't rotate, so you don't have this mode. You don't see this. A2 double prime. Hey, wait. Let me see. Did I make a mistake? Let me see. Let me see. I mean, there are silent modes in crystals. Okay. There are. Okay, but I'm not sure whether I make a mistake or not. Let me see. A1 E2 prime. This is 2. This is 1. Okay, so that's also right. You have this one. So you have. By the way, there's a prime here. I forgot. That's why I'm missing the prime all the way. A2 double prime. Oh, okay, it's here.
Like you need to see double prime.
Double prime. Okay, so the mistake is made here. The mistake is made here. Okay, my mistake is this one. Okay. So this one is not a silent mode. It's not a mode. Okay, there's no phonon mode with this representation. Okay, that's the answer. Okay, I correct myself. And if there's a mode in this, it will be silent. Okay, You just know how to apply the character table. Okay. So this E prime, is it Raman or infrared? Huh? Yeah, both. Okay, very good. Okay, you're learning. Okay. Both. Okay, this is not a mode. Is it okay? This is not a mode. So is this a Raman mode or an infrared mode? Okay, this will be infrared. Okay, what about E double prime? Raman or infrared? Yeah, this will be Raman. Is it okay? Gradually you're learning. I mean, it's not difficult. It just need to know the rules and just practice. Okay. So, okay. So if you draw the Venn diagram, you use your common knowledge, you would be able to visualize what the phonon band structure look like. First, you have 3 phonon modes. They all have a 0 frequency. However, 2 of them are degenerate due to symmetry. 1 is not. And this one, from the symmetry group, you know this is Z. This will be XY. I think so, right? E prime is XY, right? This is Z, right? Okay, so you will expect the Z and XY will behave differently. So you will expect something go up like this, and the other two is somehow more close to each other. Okay, because after you go away from gamma point, they will break the symmetry. But because these two are related to symmetry, they won't be broken so fast. This one is Z. This one is XY. So you expect a dispersion like this. Okay, when you go to up high there, you will expect one, maybe another one. I mean, the position probably doesn't matter. But then here you have 2 degenerate modes. So you expect something like this. You expect something like this. E prime. So you expect the phonon band structure will look something like this. Is it okay? Is it okay? So usually these 2 mode people, we give them the name. By the way, you can actually know the A2, this is Z. A1, this is Raman. I don't know this. E prime. This will be XY. Okay. So you expect something like this. You expect something like this. This A double prime will be Z. This E prime will be XY. So you will expect this one will vibrate in the XY plane. This one will vibrate in outer plane. Okay. So this is what you can see from the character table. So because I want to show you what you can know from the character table, even without doing any calculation on the exact Raman mode. Okay, this is the power of group theory. Of course, later I'm going to show you the exact mode. What do they look like? But even without looking at them, you can already have this much knowledge on the phonon band structure. Is that okay? Like you know how many modes, the symmetry properties, and which mode are Raman active, which mode are infrared active. Okay. Okay, so now let's look at the band structure, the real one. Okay, this is the calculated one. You can see how much I can predict well. Okay, I predict something like this. I did something wrong. Because I make the Z go up and the other could go down. Okay, I try to correct myself, and in the correction process, I want to tell you the limitation of group theory. Okay. Group theory tells that this mode will behave differently from this, but it doesn't tell you which mode go up, which mode go down. So in reality, this 2 mode will go up, the Z mode go like this. So group theory does not tell you the relative energy position. Okay, so I guess it's something like that, but in reality it's something like that. But still, my main prediction is that this 2 will behave differently. So this part is still correct, right? Okay, so we call this the ZA, this LA and TA. What do you mean? This is called the ZA mode. Z basically means the Z direction. the Z direction acoustic mode. A means acoustic mode. Okay. So this is called LA and TA mode. A means acoustic, L means longitudinal, T means transverse. Okay, these are the two modes. They will be degenerate in gamma point. When they go away from gamma point, they slightly become different. Okay. So now let's look at this structure, E double prime. Okay. So he has a E double prime here. I look at my prediction. I do have a E double prime, look like that. Okay. And then you go up, you have a E prime, degenerate and started to, you have a E prime. Okay. I also have this one. Okay, I guess correctly. And then when you go up, you have A1 and A2 double prime. So you have A1 prime and A2 double prime. Okay, I make it wrong that the relative position is incorrect. But group theory never tell you the relative position. Which one is higher, lower? It doesn't tell you. So it's actually all three, this relative position I just guess. It turned out that is not correct, but I get the degeneracy properly. Okay. Is that okay? Any questions? Okay, so now let's continue. So this is the decomposition that we just did. Okay, this is the exact not exact. I mean just the sort of illustration of the displacement vector. Okay, so let's look at the A1. It should be A1 prime. The prime is missing. What is A1? A1 means the MO atom does not move. The two S atom, one move up, the other move down. Okay, you can see that in this whole process, the whole symmetry of the crystal does not change because it's stretched like this. All the rotation, reflection, they're all preserved. So this belongs to what? The identity representation. So A1 is the identity representation. Okay. When you go to A2 double prime, what is A2 double prime? A2 double prime means all of this go to the same direction. So let me see, A2 double prime. Now this is A2 double prime. All of them go to the same direction. So that is a acoustic mode. But you also have the one for optical mode. You also have the one for optical mode. And let me see, how does it work? Let me see. I think this only shows the acoustic mode. There should be the one for the optical mode. Yeah, this is a translation. It doesn't show the A2 double prime mode. Okay, let's go to E prime mode. E prime mode. This is just acoustic. Just the acoustic. Okay, the E prime mode is these two atoms move in one direction horizontally. This one, the MO atom move in an opposite direction. Okay, so this is here. And then you can already see that if you do a mirror reflection, it is 1. Because up and down are exactly the same. Okay, so if you look at the character table, E prime, you look at this sigma H, it is 2. Remain the same. Okay. And then this is a E double prime. E double prime is this middle atom does not change. This atom move in one way, the top atom move another way. Okay, so these two, if you do the reflection, horizontal reflection, it will be opposite. It will become negative. Okay, so you check the optical table. This one this is -2. Okay, so this is the correspondence between the mode and the symmetry. Okay, I mean there are some methodology that you can deduce this normal mode vectors based on the group theory. Like you have a group theory, you do more. The group theory will help you to find the normal mode more efficiently. Okay, more efficiently. I don't know the one for this mode. I think this one is showing the ZA mode. This is the certainly the translation because I copied this from the internet. I didn't double check whether they're correct or not.
If we suppose that A to the prime as the optical component, then that arrow should be different.
Let me see. I think this one should point down. Yeah, I think the mode should be like this. I guess. I think I mean, you can already see from this go up and then this go down. This still have the Z representation, Z, because you flip it, they all become negative. Okay, because you look at A. Now you look at A2 double prime. You look at the character table A2 double prime. You have a reflection is negative, right? You have a negative, right? So this one also have negative. So you have two acoustic mode, optical mode. Another one is this. The other one is MOSS. Yeah, the other one is like this stretching. This is the A1 prime. This is the A2 double prime. I think so.
So is this A2 double prime to satisfy every symmetry that?
I think so. I think so. Is it correct? You can do this as a homework to confirm it. Yeah. I mean, we know there's an A2 double prime mode there. A2 double prime mode. And you can know why it is so high in energy. Why is it so high? Because you're stretching the strong bond. Because you're stretching the strong bond. Yeah, I guess correctly, right? Like because this is the strong bond. You're stretching the strong bond in the most distorted way. So that's why the energy is high. Okay. The other one is this is acoustic mode. If they all go up, this is the acoustic mode. So this PowerPoint is not. I mean, I copied this from the internet. I didn't double check it. This arrow should point down. That will be acoustic mode. But you have an acoustic mode here, and you have an optical mode here. They have the same symmetry. Okay, but a different vector displacement. And if you check the character table, this one a Z. So basically implies that all the atoms are moving in the Z direction. All the atoms are moving in the Z direction. Otherwise, I think it's quite difficult that they transform like a Z if they don't move in the Z direction. Okay, so if you get used to this kind of a character table, I mean, I'm not very familiar with the character table either. But I think if you do more exercise, you can get more and more familiar with it. So when you read the paper, you see a phonon mode in the paper, and it has a certain symbol, let's say E1, E2G, E2U. You go and check the character table. Just from this character table, you have a sense of what the phonon looks like. Okay. So now let's go back. It's already 2 hours. So let's go back to check the ammonium. I missed this part. Yeah, I missed this part. This is the ammonium. Okay, let's go back to check how the symmetry predict. Okay, so this is the ammonia. Where's the decompose? Okay, here. The ammonia has a 6 phonon mode. 6, okay, because these are 2D representation. So you basically you expect 4 frequencies for the ammonium vibration, because 2 of these frequencies are twofold degenerates. Okay, so let me show you the animation. Okay, yeah. Okay, these are the animations. You can see this is A1. This is the representation. This E is the representation. Okay, so these are the frequency. So this is A1. This is called the stretching mode. Okay, basically just like this. Okay. This is these two are degenerate. They're connected by symmetry. So you see the frequency, they're exactly the same. Okay, they're exactly the same. And you can see Raman active and infrared intensity. That means all of them are Raman and infrared active. Okay, this one is whacking mode. It's like this. It's like this. Okay, they're doing exercise like this. It's also A1 symmetry. That means it has the identity representation. Basically, what they're stretching is just like this, but the symmetry of the whole thing in the whole process does not change. Okay, they're just changing the length of the bond and the angle of the bond, but the symmetry does not change. So both of these are A1 and A1. Okay, you have two mode, like what I show here. You have two A1 mode. Okay, so these two, I don't know how to represent it. Something like this. Okay, they're connected by symmetry. That means when you have one mode, you do a certain symmetry operation, you will get another mode, and they're E. Okay, they call scissoring, like scissoring. Is that the scissor? Okay, so if you want to look at it more carefully, there's another page. Okay, this one you can actually. Okay, look at the A1 mode. Okay, this is called the bending mode. You see the frequency is the lowest because you are not changing the length of the bond. You're just changing the angle. And I mean, you can easily see, right? If you have something, okay, if you want to stretch it, you take more energy, but you want to bend it, you take less energy, right? You just use classical mechanics, common sense. You know this one does not take as much energy, so the frequency is low, and it's called the bending mode. You can see the whole process. The symmetry of the molecule does not change, so that's why it is an identity representation. Okay, you go to another stretching mode. This is like this. You can immediately see the frequency is much higher than this because you're changing the length of the bond. It takes more energy. Okay, then you go to the bending mode. This one is like this. Okay, and then this one is something like that, but in another direction. Okay, so these two are related by symmetry. They all have the same frequency, and you can see that the frequency is also not high. Why? Because you're still changing the angle of the bond. The length of the bond does not change. Okay, so but it's higher than this bond. Okay, and then this is the stretching one. This will be how does this change? I cannot quite visualize it. But since it's stretched, I suppose the band length should change. Let me see. Does this angle look better? Okay, yeah. You see, this is the stretching one. The length of the mode actually changes. Okay, the length of the mode changes. This one only changes the angle. This one looks. Why suddenly it slowed down? Okay, there's some automatic change of the speed. Okay, this one changed the length. That's why the frequency is so high. This one changed the angle, so that's why the frequency is relatively. What happened? Okay, it's hiding. Okay, very mysterious. Okay, this page. Okay, so you kind of get an idea that how do you connect the representation to the actual mode, and also how you like kind of interpret why the frequency is high is low from the configuration. Okay, I think it's actually quite interesting. If you want to display the vector, okay, yeah, this one show the vector is actually changing in length. This one, well, people really spend some nice effort to make it visualize to us. Okay, okay, very interesting. So, okay, so I hope through this lecture you have some knowledge how to connect the representation to to the configuration and how to interpret whether it's Raman active or infraactive. Maybe the next lecture I can talk a little bit more about what is Raman active, what is infraactive, how they're related to the configuration. But the method here I already show you. Yeah. So it's pretty, after you know the result, it will be pretty straightforward to represent. Basically, every time you deal with a new material, check the symmetry character table, get all the phonon modes. Usually people already did it for you. When they publish the paper, they already have that. You just need to interpret it, like know the language to understand what they're writing.